Okay, we have here today another integral. This one's from the UK integration bee. Sample problem number 1. We have the integral from 0 to 1 of x to the 5th minus 1 over ln x dx. Okay, when I started on this, I was messing around with this, trying to get a u substitution, maybe some factoring, but nothing was really working. But what I found we could do here is we can rewrite this as a function of t, introducing t into this when I rewrite it. And what I'm doing is I'm focusing on this exponent 5 right here. So if we have an integral going from 0 to 1, I'm going to write this as x to the t minus 1 over ln x. So now we have two variables inside the integral. We have this whole thing as a function of t. What this is going to allow me to do is now let's just integrate it and find a value for f prime of t. So to do this, on the right side, what we're going to do is we're going to differentiate with respect to t, and we're going to have all this stuff come over. But for this right here, what we're going to need to do is we're going to need Feynman's trick in order to differentiate inside the integral sign. So in order to do this, coming over here, what's going to happen is we're going to bring it inside the integral, but write it as a partial with respect to t, integrating all this stuff within the parentheses. And then what's going to happen is all of our x terms are going to become constants, and it's going to allow us to get some simplification here. So doing this derivative, coming over here, what's going to happen is this ln x right here, that again is a constant value when we're differentiating with respect to t. So I'll bring that out front here, not outside of the integral, because the integral is with respect to x, just outside of the derivative. We'll bring this out as a constant. Then just focusing on differentiating this with respect to t, for x to the t, I can rewrite that as e to the ln x, bringing the t over here. We'll still have this minus 1. When we differentiate this with respect to t, well, the minus 1 is just going to be a 0, so that's going away. We're going to have this same term repeat. We'll have e t ln x. But then chain rule on this right here with respect to t, this is just a constant, so we'll have the natural log x come out front. But then I can take this here and put it back the way we had it there. And so we can write this as natural log x times x to the t. So copying this over here, we're going to have our ln x times x to the t dx now. But now at this point we get the simplification we need because the ln x's cancel, and then we can just differentiate this. But again, now in the integral, t is a constant value, so we can just use power rule on this. So we'll just go ahead and integrate. Integral here is going to give me x to the t plus 1 over t plus 1, just evaluated from 0 to 1. Evaluating this, plugging in 1, we're going to have 1 to the t plus 1. That's just going to be a 1 over t plus 1. Then for the second part, when we evaluate at 0, this is just 0, so we'll leave it like this for our f prime of t value. So then this is some good progress, but really keep in mind our goal is this is our original integral, and this is the same thing as f of t evaluated at 5. You plug 5 in here, and this is the same as the original integral. So what we need to do is take our f prime of t and get it back to f of t. And so what I can do for that is just integrate it on both sides here, integrating with respect to t now. Because this is a derivative, this is just going to be the same thing as f of t over here. But now this is going to be an easy integral to do. This is just going to give me natural log absolute value t plus 1 plus c. But now we don't really want this plus c here. We have a definite integral. We need to get this to a numeric value. So we need to do something with this. One thing I should have mentioned when we set this up is we need some value of t where we can evaluate this. We're going to get a known value for f of t. Well, it turns out a good value here is going to be when t equals 0. For our f of 0 value, when you plug a 0 in there, x to the 0 is going to be 1. The numerator becomes 0, so the whole integral is 0. So we know that our f of 0 value is going to be just 0. So we can take this and we can use it right here. So for our f of 0 value, just plugging 0 in here, we're going to have natural log absolute value 0 plus 1. We don't need absolute value really, but whatever. Then we'll have the plus c, and we know this is going to equal 0. Well, natural log of 1, when we simplify that, that's just going to be 0. So what we're saying here is that we just have c equal to 0. So what that allows me to do is just kind of get rid of this plus c right here. And then we have this ln t plus 1 value, and this is going to be our f of t. So now the only thing we need to do to finish this off is just evaluate this f of t at a value when t equals 5. So we just need the f of 5 value. Plugging 5 in here, we're going to get natural log of 5 plus 1. Putting it together, the final solution of this is just going to be natural log of 6. Okay, there you have it. Really good problem from the UK integration bee. Thanks everyone for watching. Have a good day.